the shape is very, very funny, strange. And this is due to a plasma on the Jupiter. It's a simulation of the plasma, and you see some plasma features on the Jupiter, and the radio observation detect this kind of plasma. And you saw already this image this morning. What is this? You saw 30 minutes ago. What? Yeah, it's easy. Yeah, round shape and ring. Certain. Right. Next question. What is this? I expected, but it's wrong. Also, this is a radio image of what? You know? Supernova. Also, it's a gas expanding in the interstellar medium. But it's very strong energy so that you can observe in radio. Also, sometimes you see in optical range. Does it mean? Centaurus, constellation Centaurus. There is a very big galaxy. And it's a montage of X-ray image, optical image, and two of radio images. It's a continuum, say, okay, anyway, radio, and another radio image at 21 centimeter. Also, you heard this morning, 21 centimeter. I didn't understand what he explained on this. You remember? 21 centimeter wavelengths at radio can detect the hydrogen in the universe. Hydrogen is the most popular atom in the universe from the beginning of the universe, and still remain. And you see the similar shape because it's a dark image, means a dust in a galaxy. And dust was formed by hydrogen, so that the shape was similar. But it is this shape and this. It's very, very different. And what I'm talking later on this shape. This is called jet and lobe radio observation. And the size is very, very large in linear size, linear means actual size. But on the sky, it extends 10 degrees. You know the size of the sun. What's the size? In angle. What is the size? In angle. 0.1 degree, 0.5 degree. And 20 times of the size. Of course, apparent size. Very large. And also, actual size is 0.8 megaparsec. Sorry. how much in parsec? Oh, light years. I ask your teacher later. Million parsec. Million light year. Roughly million light year. You see the optical image. It's a galaxy. A little bit funny shape, but very small. And linear size is 1 megaparsec. 3 million light years.
300万光年。
But again, it's floating out, and black hole might be here, but it's very, very small. We cannot see until now the black hole. But this very, very huge jet, energetic jet is produced by a black hole here. Okay, it's a schematic diagram. Black hole here, and around it, accretion disk. And torus is rotating again. And the rotation in some core is a common phenomenon in the universe. We are also running around the sun, and sun is running around the galactic center, and these materials also are running around the black hole. It's due to the gravity. Understand? Attract the things. But as you may know, black hole has a very, very strong gravity. And okay, due to the strong gravity, the black hole attracts many, many materials. And we don't know why, but anyway, as you saw, the jet is running out somewhere from the black hole. Of course, it's not the observable image. Accretion disk rotating along the black hole. Black hole should be there, and something is running out. Why? So black hole create the huge energy that, as I told you, black hole has very strong gravity force, and materials around the black hole is attracted, and collide with each other, and due to the very high density and high gravity force, the temperature is getting higher and higher, around several thousand degrees. And very strong things should happen, but we don't know what is happening because we cannot observe yet because it's very small. So how to see supermassive black hole? Supermassive black hole size is very, very small. So we need high angular resolution telescope. And angular resolution is proportional to wavelength divided. When you want to get eyesight 1, What is the diameter? Suppose wavelength is 10 to the 5 times different. So diameter is 10 to the 5 times, what, 4 times? So 2 millimeter times 10 to the 4. Several hundred meters. 200? Okay, something like that. It's easy so. Okay, what I would like to say is a radio telescope has a very, very bad eyesight. Even your naked eye has usually eyesight 1. How should we do to see the black hole? It's very, very simple. How small? One part of millions of eyesight. To increase the eyesight, as you see, we have a large aperture distance interferometer, as you saw again with Alma. We are building this system in Chile, high mountainside. This has several million eyesight. But even so, not enough. So what we should do is to extend the size. But when you extend
拉长
you may have error of between the signal from here and here. And accuracy should be 120. So if you want to observe it 1 centimeter, 0.5 millimeter, we need the baseline length several hundred or 1,000 kilometers. But you have to keep the length in point, say 5 millimeter. It's almost impossible. So that Vlbi gave up to connect each element. But instead, what we do is to record the data on a magnetic tape in the old days, but nowadays in the hard disk. And after the observation, we send it to one station, correlation center, to collate to get the interferometer. This is a picture also you saw in the United States, 25 meter dish in Hawaii and Puerto Rico and North America. The out size is limited. We cannot extend that 12,000 kilometers, which is the diameter of the Earth. If you want to stretch the baseline, you should launch a telescope in space. Actually, we launched this telescope in 1997 from Japan. and it worked. Okay. And one telescope in space is cooperating with the telescopes on the ground, and the baseline length is more than the diameter of the mirror, which means you get very small. But even so, we cannot see the black hole because it's too small. And here you see our project in this institute to set one telescope not in space but in Greenland, collaborating with ALMA in Chile, and there is also a radio telescope in Hawaii. But also we are using very short wavelengths, 1 millimeter or much shorter, with almost the baseline of the Earth diameter. And here you see the site in Greenland. Of course, it's covered by ice, snow. And here is a black hole image we are expected to look. This is a simulation. But why it looks like black hole here and accretion disk here. If you are looking here, the accretion disk is very bright. As I told you, it's very hot. Temperature is very high. And far side of the accretion disk is the light is bent due to the very strong gravity of the black hole. And this side also the light is bent a little bit. And black hole itself is a black, so no light from here. But against the very bright accretion disk, you see the black shadow, actually black hole in the image. So if you see a black shape in a very bright disk, it's a black hole. But no one ever sees yet. So what we are trying to do is to see this black hole. And there are many simulations there. If black hole is rotating, the shape might be. And depending on the accretion disk, the shape may change. And several, many simulations also. In addition to set very high angular resolution Vlbi system. I told you. One very interesting target is this one, M87. It's a galaxy, a radio galaxy. And this size is milli-arc second. 1,000 of arc second. Arc second is 1/60th of arc minutes, and arc minute is 1/60th of arc degree. Very tiny. The eyesight is 100 of 1 million or more. Okay, so no one knows, but we are expecting a black hole here, and should may have black shadow image, which we are expecting to see by the sub-millimeter Vlbi system. Okay, thank you. Question?